So in this video, we're going to look at the properties of alkanes and of alkenes. And we're talking about properties. We're typically looking at the boiling points, the conductivity, whether or not they conduct electricity, and their solubility. So we're going to start with boiling points. And I've just sketched out this rough diagram of methane as a solid, methane as a liquid, and methane as a gas. And you can see that when I go from solid to liquid to gas, that I still have carbon bonded to 4 hydrogens. The formula, CH4, is the same whether it's solid, liquid or gas. You've still got a carbon bonded to 4 hydrogens even when it is a gas. So to get from a solid to a liquid to a gas, I am not breaking those carbon-hydrogen covalent bonds. No covalent bonds are being broken. Instead, I'm breaking the forces that exist between the molecules, which are the intermolecular forces. So each one of these CH4s is called a molecule. And when I go from a solid to a liquid, I am breaking these intermolecular forces so that I can move the molecules further from each other. When I'm going from a liquid to a gas, I'm fully breaking these intermolecular forces to fully separate out these molecules. I am not breaking the covalent bonds between carbon and hydrogen. Carbon is bonded to 4 hydrogens in a liquid. It's still bonded to the 4 hydrogens when it is a gas. So when you're answering these questions, you should not be mentioning the covalent bonds at all. You're focusing entirely on breaking the intermolecular forces. There are 3 types of intermolecular forces. There are London forces, there are permanent dipole-dipole, and there are hydrogen bonds. When we're looking at alkanes and alkenes, the only atoms that you've got present are carbon and hydrogen. Carbon and hydrogen have got similar electronegativities, therefore there is no permanent dipole. There is also, you don't have a hydrogen bonded to a fluorine, a nitrogen or oxygen, so you've got no hydrogen bonds. The only intermolecular force you've got present are the London forces. So that's what you're going to be talking about when you're talking about the boiling points of alkanes and alkenes. So if we look at an example, I'm going to draw out my standard alkane. I'm going to draw propane. If I had a container of propane, I would have lots of propane molecules. If I wanted to boil propane, for example, and turn it, so if it was in liquid form and I wanted to turn it into a gas, I would need to separate out these propane molecules. I would need to overcome those London forces because they're the intermolecular forces existing between them. If I compare propane to pentane, okay, I've got a similar story. If I wanted to boil pentane, again, I would need to separate these pentane molecules and I would need to overcome the intermolecular forces holding the pentane molecules together. But your typical question will ask you, well, which is easier? Is it easier to separate propane molecules or is it easier to separate pentane molecules? The answer is it's going to be easier to separate propane molecules. It'll be easier. Therefore, you need less energy and you're going to have a lower boiling point. The question is why? It's to do with the length of the chain. In pentane, the chain is longer. Because the chain is longer, you have got more points of contact between the individual molecules. More points of contact means you've got more London forces to overcome. Okay, if I compare that to propane, because it's a shorter chain, there are not as many points of contact. I don't have as many London forces to overcome. So it's got less energy required. It's got a lower boiling point because you've got fewer points of contact, meaning you have got fewer, or you can say weaker, London forces. In general, the longer the chain, the more points of contact, the stronger those London forces are going to be, the more energy needed to break them, the higher the boiling point. As well as talking about the points of contact, you can also just talk about the number of electrons. The more electrons, the stronger the London forces. Because this is a longer chain, you have got more atoms, you've got more electrons, you've got stronger London forces. The other thing you can be asked to compare is if I had two molecules that were the same size, but one of those molecules had a branch and the other one did not. Because these molecules on the left have got a branch, they don't fit together as nicely, okay? Here, when you've got a nice, just unbranched chain, the molecules can sit together quite tightly and quite compact. And that means you're going to have more or stronger London forces. Over here, because of the presence of the branches, they just don't sit together as nicely. The branches get in the way and they stop the molecules sitting together as nicely. Because they don't sit together as nicely, you end up with fewer points of contact and fewer weaker London forces. So over here, you would have a lower boiling point. Lower boiling point because of the branching means you have got fewer points of contact, therefore fewer or weaker London forces. If we just look at one more example, what about comparing this to this? So here I've got an alkene and here I've got my alkane. Which one's going to have a higher boiling point, my alkene or my alkane? The answer is going to be the alkane. This has the higher boiling point, and the reason is the same as what we saw below. Okay, the chain is longer. It's got a longer chain, therefore it's got more points of contact, therefore it has got more or stronger London forces, which require more energy to overcome. But what students often do is they see the double bond and they focus on that. And they typically write in their answers, oh, the alkane is a higher boiling point because of that strong covalent bond. But remember, sorry, that strong double bond. But remember, you're not breaking the covalent bonds. When we went from a solid to a liquid to a gas, we were not breaking any of those carbon-hydrogen bonds. And it's the same here with the alkene. You're not breaking that carbon double bond carbon. So it doesn't matter how strong it is. All you're doing is separating the individual molecules. So if I want to boil butane, it doesn't matter that you've got that double bond there because you're not breaking it. All you're doing is separating out the two butane molecules. All you're doing is overcoming the London forces. Because the alkane over here has got a longer chain with more points of contact, the London forces are stronger, so it's got a higher boiling point. So don't be sidetracked by the presence of the double bond. It doesn't raise the boiling point because you don't need to break that bond when you are melting or boiling an alkene. All you're doing is overcoming the London forces, and the strength of London forces will depend on the length of the chain and the branching, because that will affect the points of contact. It will also depend on the number of electrons. The more electrons, the stronger those London forces will be. I want you, oh no wait, sorry, I'm going to talk about solubility first. In terms of conductivity, for something to conduct electricity, it needs to have charged particles that can carry current. So you need charged particles to carry current. When I'm talking about charged particles, I'm talking about ions that can move freely, or I'm talking about delocalized electrons. Alkanes and alkenes have neither. Okay, they're covalent molecules, so they do not have ions. They also do not have delocalized electrons. So your alkanes and alkenes do not have charged particles to carry current, therefore they do not conduct electricity, and it's as simple as that. In terms of solubility, and we'll look specifically at solubility in water, for something to be very soluble in water, you want it to be able to form hydrogen bonds in water. So to form hydrogen bonds with water, you're looking for the presence of an OH or an NH or an FH. Alkanes and alkenes have none of these things, okay? They don't have any oxygens, nitrogens, or fluorines, therefore they are not going to be able to form hydrogen bonds in water, and your alkanes and alkenes will both be will have very low solubility in water. Anytime you're asked about solubility in water, the main thing you're looking for is, can it form hydrogen bonds with water? Alkanes and alkenes cannot, therefore they are going to be pretty much insoluble in water. I want you to have a go at section C from your feedback sheet, properties of alkanes and alkenes. I want you to explain. When you are explaining, you have to tell me, you have to use the following terms in your answer each time you explain. I should see the words London forces. Just saying intermolecular forces is not enough. I should see the word London forces. I should be seeing points of contact. And I should also be seeing the word energy. You always get a mark for energy. Make sure you've got the word energy in your answer. So the first three questions relate to boiling points. So these are the terms I should see. In questions 4 and 5, you're talking about solubility. It's only for 2 marks. And you need to comment on whether there are any groups present that can form hydrogen bonds with water. So press pause, have a go, and then press play to see the answers. Okay, so again, I've done the answers here on my iPad. So the first one, I'm comparing A to B, which is the higher boiling point. The answer is B. You have to explain why. It's got a longer chain, so there are more points of contact between the molecules. Make that clear that you're talking about the forces between molecules. You shouldn't be mentioning covalent bonds in your answer at all. So longer chain, more points of contact between molecules. So therefore you got stronger, or you can say more London forces, which will require more energy to overcome. So I'm mentioning the longer chain, more points of contact, stronger London forces, more energy to overcome. In 2, so I don't know where my molecule A is gone, but it's got a little branch on it. And the answer is again going to be B. And the reason it's B is because it's unbranched, whereas A had a branch. So I'm saying it's unbranched. So there's more points of contact between molecules, resulting in stronger / more London forces, which will require more energy to overcome. So it's exactly the same as what I had before. I'm just changing the longer chain part to the unbranched part. And other than that, I'm using all of the same language. So get in the habit of using those right keywords. In the next one, I've got, and I deliberately did this, I put 2 double bonds in one molecule and 1 double bond in the other. But remember, you're not breaking the double bonds. So it doesn't matter that there are more double bonds in A, they are not being broken. So your answer is still going to be B, and the reason it's B is you've got a longer chain, so you've got more points of contact, stronger London forces, require more energy to overcome. You could also say that B, because it's a longer chain, that you've got more electrons, which result in stronger London forces. Sorry, you could say that up here as well, that because B is longer, it's got more electrons, so stronger London forces. 4, we're talking about solubility. Okay, the presence of this OH group here means it can form hydrogen bonds with water, and that's going to make it more soluble. So B, you have to identify the group, the OH group, and then say why an OH group makes it more soluble, because it can form hydrogen bonds with water molecules. And then you've got A and B again. Sorry, the answer is B and B every time. Okay, but B again has got the OH group. It can form hydrogen bonds with water molecules. So that's what you are focusing on. In general, with solubility, like dissolves like, so something polar dissolves in a polar solvent, but that's only weakly true. It's a general rule, but there is more to solubility than that. So rather than just talking about polarity and like dissolving like, focus on groups that can form hydrogen bonds with water, because that will be your answer. That's what they're going to want to see on the mark scheme. In the next video, I'm going to go through section D, which is reactions of alkanes.